Hello, everyone. In this video, I wanted to go over a particular problem that one of my students happened to be struggling with. He asked me for help, so I decided to make a quick video solution to this problem. So the problem is on the right of the screen. It's an SAT math problem. We're doing number 23. That's the one he requested help with. And this problem is a data analysis problem. Specifically, it deals with linear regression. And for those of you who have never heard of that before, maybe those of you who aren't familiar with it, regression is a term in math that means we are taking some data. In this case, we are taking this data right here, and that we are examining the relationship between these data values and these data values. There is some kind of a relationship. It's either going to be a really loose relationship or it's going to be a really tight relationship where there is a perfect one-to-one correspondence. We have an exact equation we can use to get from this value, for example, to this value, and then from this value to this value. So if it is an exact one-to-one correspondence, there is no need for regression. We can just come up with our own equation that can help us perfectly model this data. Otherwise, we have to use regression. Regression helps us make sense of imperfect data. It helps us create a somewhat perfect model for imperfect data. And for example, suppose we have data values that look something like this. This isn't what we're given. This is a completely random, different example, but I feel like it'll help me illustrate my point a little bit better. So suppose we have these data values right here, and we want to create a relationship. We want to create a one-to-one correspondence that loosely fits this data. So a line of best fit would be something like that. We want to get a line that is kind of in the middle of the data, something that kind of represents the average of all the data values. If we had something like this wouldn't be very good. If we had something like this wouldn't be very good. We want something that's kind of considered to be the middle of all the data. And that's why this right here, this line is a really, really good representation of what we consider to be the middle or the average of all the data values. And this is where regression comes in. Regression helps us create a really, really good line of best fit for all the data values. But why do we even care about that? Why is this important? Well, let's say we don't have any data values down the line, but we want to create a projection of what we feel like they should be if time went on. So for example, what if we're interested in what we would expect the data to be at this particular X value? We don't have any data points, but what we do have is a line to help us figure out what we would expect it to be under these circumstances. So under these circumstances, with this line of best fit, we can expect the data value to be around here. This would be our expected value. And remember that the expected value is just a term for the average. So this would be our expected value. We don't have any data points to help us extrapolate that information, but what we do have is a line to give us that expected value. And that's why regression is such a powerful tool to have in your arsenal. So onto the problem. The Townsend Real Estate Group invested in 5 different properties listed in the table above. The table shows the amount in dollars the company paid for each property and the corresponding monthly rental price in dollars. The company charges for the property at each of the 5 locations. And then we're going to look at 23. The relationship between the monthly rental price R in dollars and the property's purchase price P in thousands of dollars can be represented by a linear function. Which of the following functions represents the relationship? So linear regression is going to help us create the function. We have no idea what it could be, but we're going to use Desmos, this nifty graphing calculator tool I have open on the right side of my screen, on the left side of my screen, to help us create that equation. So what I did is I already inputted all the data values. So the purchase price in dollars would be all of our X values, and then the monthly rental price would be all of our Y values. So Desmos is a really, really powerful tool in this case, because what it can do is it can take all of these values and it can create an equation that best fits all of our data values. So in some cases, the line of best fit is just a line. In some cases, it's going to be a parabola. In some cases, it's a hyperbola, some pretty crazy stuff. But in this case, it's going to be just simply a line. And the equation of a line is y equals mx plus b. We have a lot of y's. We have a lot of x's, but what we don't have is an m, which tells us the rate of change along this line of best fit. And we don't have a b, which tells us where it starts on our y-axis. Both pretty important bits of information to have. So I'm going to see if Desmos can give us that information. So like I said, it's a line. So our equation is y equals mx plus b. Excuse me. Sorry about that. But what we need to do is, instead of it being equal to mx plus b, we need to change it so that it is approximately equal to mx plus b. Because remember what I said earlier about this not being an exact equation. It's not fitting all the data values. It's just an approximation. It's just a line of best fit. It doesn't actually go through all the data points. So that's why instead of equals mx plus b, we have this little squiggly thing, this tilde, which means it's approximately equal to mx plus b, because it's not an exact fitting line. And then there are a few other modifications I want to make here. So I'm looking at the table. I see that at the top, we have y sub 1. So I want this to also be y sub 1. And then I see at the table, we also have x sub 1. So I want our equation to reflect that. I want us to also have x sub 1. And notice how it spits out some information right away. We're going to ignore the r squared and the r. We don't need that. We don't need the residual either. What we really need is this information down here at the bottom, the parameters. We have what I was talking about earlier. We have our slope, m, our rate of change, and we have our b, our y-intercept, which is exactly what we want to have. So that means in this case, our equation would be y equals mx plus b. So that would be 0.0075 times x plus our value of b, which is -10. So that turns into -10. But we're missing something here. Let's go back to the problem. It mentions that the purchase price P is in thousands of dollars. So we need to reflect that in our final answer. So that means instead of it being 0.0075x, it's going to be 7.5x when we move the decimal place the appropriate amount of times to reflect the fact that our purchase price is in thousands of dollars. So this is our new equation. And again, this isn't an exact equation. We can plug in an x and get an exact y. It only gets us an approximation because that's the nature of any kind of linear regression situation like this one. All right, hope you found this helpful. Yeah, I know I've been absent for a while. I've been really busy, but hopefully I'll be a lot more active in the future, making a lot more math videos, maybe some chem, maybe some physics. So look out for those in the future, and hope you guys have a fantastic week. See you next time.